We have seen that all the types of efficiencies and all, and we have seen the performances criterias and all. So we have skipped this particular graph, and what does it explains. So we will look into the significance of that. Okay. So you can see in this graph that specific impulse and it is with respect to flight speed. Specific impulse with respect to flight speed. And here we have seen the specific impulse versus flight speed. Here we have sigma. What is sigma? Sigma we have seen it is in the speed ratio. Is the speed ratio. Okay, that means VA by VE. Okay, flight speed with respect to the jet speed. Okay, and eta P shows that it is the propulsive efficiency. Eta P represents the propulsive efficiency. Okay, now what we can say, what the significance factor we can bring. Now here we have this curve, we have 0.10. Here we have sigma is 0.90 and eta P is 0.947. Okay. Now can I say that as we increase in flight speed, okay, as we increase in flight speed, what is happening with the specific impulse? It is increasing. It is in an increasing order as I'm increasing the flight speed. Now one more thing it has to note that this figure shows that when the flight speed ranging from 200 km per hour to 2020 km per hour. Okay, so it is not from the zero, the velocity is not from the zero. So when it is ranging within this limit, right, when increase in flight speed, the specific impulse is also increasing. Now coming to the point, how it is affecting with respect to the speed ratio and the propulsive efficiency. We can say that as the propulsive efficiency increases, which way it is increasing? Can I say propulsive efficiency increasing in this order? So gradually it is an increasing order. This is an increasing order. That means here we have 0.18. Gradually it is increasing to 0.947. Now what will happen where if eta P is 0? When the eta P can be 0? Where the eta P will be 1? At what point the eta P will be 1? Where it will locate? If eta P has to be 1, that is eta P, what is eta P? Twice of sigma by sigma plus 1, or I can say 2 VA by VE plus VA, right? And what is sigma? Sigma means
it must be equal to 0.5, ma'am.
Yes, it has to be.
It has to be 0.5 for eta P to be 1.
Eta P to be 1 means if the eta P has to be 1, then how much the value? 2 VA.
It's 0.
Sigma 2 sigma by sigma plus 1. What will you get? Sigma plus 1 equals to 2 sigma. So what you get? 1 equals to sigma. Am I right? That means VA has to be equal to VE.
Oh, sorry.
Hannah, right?
Yes, ma'am. Yes, ma'am. You're right.
Okay. So to get the maximum amount, the VA has to be equal to VE. On that situation, that means it will be lying, if eta p has to be 1, it will lie on the along the x direction. It has to lie along the x direction. So this is another one of the significant point. So as our, okay, now this is one of the point. Now what will happen on the same scenario? Same scenario, what will be happening with our specific impulse? Specific impulse is also going down. What does it mean by specific impulse, which is also can be termed in terms of specific thrust? Okay, it can also, we can say, as a specific thrust. Okay, Fs. What is the difference? Let's recall, F by m dot a. Okay, this is the specific thrust, and specific impulse is F by m dot a into g. That is a difference. Now the same way we can also note for the speed ratio. As the speed ratio gets 1, right, the specific impulse will also lead to be 0. Specific impulse also decreases. Okay, this is one of the significant point. Yes, similarly you can see the how this SFC varies with different kind of Mach number and different kind of engines. So as we increase the Mach number, the SFC also gradually increase. This is another statement. As we increase the Mach number, right, the SFC gradually increases. And among the all, which is having the highest SFC? Among the all, which is having the highest SFC? Can I say afterburner turbojet having the highest, then I can pick the ramjet, then turbojet, then gradually the other engines, right, gradually the other engines. So yeah, one more important concept from the turbojet cycle performance. This is a graph between specific thrust on this side, on the x direction, and SFC in the other direction. SFC in the other direction, and they have plotted this graph between various kind of compressor pressure ratio, that is RC, and turbine inlet temperature. Turbine inlet temperature. Now it is a very important thing to remember this. Okay, the main parameters, the majority of the parameters, what we want to improve the efficiency. And how we can improve the efficiency? By keeping a moderate and optimized compressor pressure ratio or the turbine inlet temperature. Okay, now see how this graph shows. Okay, now first let's see for the turbine inlet temperature. Now these are the values which you can see over here. These values are the turbine inlet temperature. Okay, now first let's consider for the line for the 1200 Kelvin. Okay, the first one, 1200 Kelvin one. So if I consider that one, this value, what I can understand in this, if I have to say, from as we decrease the compressor pressure ratio, right, with change in specific thrust, it is gradually the specific fuel consumption is increasing. Okay, specific fuel consumption is increasing. Let me repeat once again. By change, or I can say by as gradually, let me take from this point to this point. So if I want to move from this point to this point, this is the point where the compression pressure ratio is 25, and this is the point. Okay, this is the point where the compressor pressure ratio is 5. This is 25, and this is the point is 5. Now as gradually I am decreasing, what I am doing, I am decreasing my pressure ratio at certain amount of turbine inlet temperature. What I can notice that my specific thrust increases. As increase in specific thrust, we can see our SFC also increases. Okay, or we can take at certain given value of turbine inlet temperature. Okay, by increase in compressor pressure ratio, what is happening? By change in specific thrust, my SFC is decreasing. This is one of the very much significant point. Okay. Now what happens as we increase the temperature, as we increase the turbine inlet temperature? What is happening as we increase the turbine inlet temperature? With the change of specific thrust, then our specific fuel consumption is also increases as compared with the lowest value. Okay, our specific, as we increase the specific thrust, okay, our specific fuel consumption is also increased as change in inlet temperature. Okay, now let's consider at some given compressor pressure ratio. Okay, now I am considering this is my compressor pressure ratio, that is 25. Okay, so gradually if I am going upward direction, my pressure ratio is decreasing. So I can say as I lower the compressor pressure ratio, that means I can get an effective amount of SFC at certain amount of specific thrust. Now you can say in this way that if I make a dotted line over here another dotted line, okay, one in the compressor pressure ratio 5 and another one is at 25. So whose specific fuel consumption is more? When we have the low pressure ratio, the specific fuel consumption will be more. As we increase the compressor pressure ratio, we will be having less specific fuel consumption. Okay, similarly now I have drawn a vertical line. Now for the low compressor pressure ratio, what we can say that the specific thrust, okay, will be more as compared with the other one. The specific compressor pressure ratio for the lowest value, okay, it will be reaching in the early point to the, as compared as we increase the compression pressure ratio, our specific thrust will be improved. Alright, just give me a moment.
You are now muted.
Okay, am I audible to you?
Tom.
All right.
Audible.
Okay. Sorry for the delay. All right. So what I was telling is that as we increase, so this is the point when we have the compression ratio is 5, and this is the point where we have the compression ratio is 25. So that means more we increase the compression ratio, we will get an effective value of specific thrust. Okay, clear? Now let's see how this factor depends with the change in temperature at a given point. Okay, at a given point, that is, let's consider the 25, when we have the pressure ratio at 25, as change in temperature, how it creates a fact. Now at this point also, we have the pressure ratio 25 with a different turbine inlet temperature. Okay, these are the points of the compression ratio. Okay, compression pressure ratio. Now what we can bring to this conclusion, that when at a given point of pressure ratio, as we increase the turbine, or I can say as I increase the turbine inlet temperature, right, what is happening? The specific fuel consumption also increase with an increase in specific thrust, Okay, now we can say in a vice versa also. Right? Once we are fixing, this is only when we are fixing the at some given point of compressor pressure ratio. There's some given point of compressor pressure ratio. This is the fact. Okay. Now these are the key parameters which will help to improve the performance. Now what kind of question you can get from such kind of thing? First of all, you can expect to get either some kind of statements. They will give you some force statement, and they will ask you find out the wrong statement out of it. Second thing, they will give that if at a given point of pressure, right, at given point of compressor pressure ratio, what will be the changes of SFC and other parameter they might have given you, maybe the specific thrust they are giving. So accordingly you have to find out. It can be the temperature, it can be the SFC, it can be the specific thrust also, right? So it can expect such kind of thing. Next, based on that, they can also show you some of graphical representation. They will give you the change in nature. It is completely clearly shown or understand from that graphs, right? So how these factors are varying with one another, which one will be the greater, which one will be the smaller, or subject to that particular thing. Or I can say like this kind of statement, that SFC for temperature SFC for the temperature 1200 will be less than SFC of temperature 1400, less than SFC, so on with the 1800. So such kind of statement also they can give, and you have to find the right answer. It can be SFC, it can be specific thrust, it can be specific impulse. In other words, they can give in specific impulse. Okay, all right. Now these graphs are very important, and they preferably ask these graphs for first section when we have 1 marks question. Okay, now these are the few graphs for the ramjet performance. It shows, the first one shows that how this the specific thrust vary with the change in Mach number. So you can see that Mach number ranges from 1 to 4. So as we increase the Mach number, it reaches, at some extent it reaches the maximum point, and gradually it starts to fall. gradually it starts to fall. And this is the nature. This is for the ramjet engine. This is, we are talking about the ramjet engine. Okay. Next we have for the TSFC for ramjet. Okay. As increase in Mach number, what is happening? As we increasing, the TSFC falls. TSFC falls. Okay. The specific fuel consumption decreases. Okay. Now from there we know the lower is a specific fuel consumption, better is the performance, or better is the engine efficiency. Better is the engine efficiency. Now again let's see what happens when the variation of fuel to air with the variation of Mach number. Now as we increase, okay, we require less amount of fuel to air fraction. The fraction gradually decreases once we increase the Mach number, right? So automatically if the requirement of the fuel fraction will be less, then automatically you can understand that in other way around, we can understand it will be having the low SFC. Your main motto of the low SFC means your fuel consumed or the requirement is less. And you can see in this parameter that here also as you increase in Mach number, right, your fuel fraction, or I can say fuel to air ratio, is also decreases drastically.
Excuse me, ma'am.
Yes, please.
I want to know what is the meaning of RD and RN, ma'am. What is the meaning of that?
Where are the
In the third graph, ma'am, in the final graph, they're given RC. RC is that RC the compression ratio? What does that mean, ma'am?
where is it RC?
On top, ma'am.
This one?
Yes, ma'am. RC, RD.
Okay. These are the efficiency. No. This is nothing with that. They have considered these parameters at certain amount of efficiency. These are the efficiency for the nozzle, diffuser. This is the efficiency for an C means
Compressor.
And this is the efficiency for the nozzle.
Okay.
Hmm.
Okay, ma'am.
When they're having this kind of efficiency, so what are the parameters? Okay. Alright. So again it comes, already we have discussed this forward speed, how it works, and yes, now another important, as I've said, we will come in the this is a part of your in your syllabus. They have asked in that just give me a moment, let me see. Okay, they have asked that in your syllabus, thrust, efficiency and range. Okay, now thrust we have seen, efficiencies also we have seen. In efficiency you can see all the Brayton cycle, and performance we have seen, ramjet, turbojet, all the things we have seen. Next comes the range. Now how this range play an important role in this gas turbine engine, right? Now what is range? First of all, though we have not covered the flight mechanics, but still you might be knowing what is range. So can you anyone please unmute yourself and say what is range?
On the distance that the aircraft that travels from the place where it takes off to the destination with one load of fuel, ma'am.
Yes, alright. So that is, this point is very important. Suppose an aircraft having a mission called from starting from the engine warm up to take off, that is climb, then cruise, loiter, descent, and till it land, right? So this is a one complete mission. So to perform this one complete mission, how much distance it is traveling, right, with an one loaded of fuel, the amount or the distance it is traveling, okay, with an one loaded of fuel. That is a very important word, one loaded of fuel. So how to judge this range? So you might be studying an equation called Brochet equation. Brocket equation, right? So where they will have some kind of factors, okay, Brocket equation, range denoted by r equals to some value of this kind of, okay, some kind of values will be there, right? Now what this explains, so that means range, okay, range is a parameter which has a direct connection with C suffix T, means is a thrust specific fuel consumption, okay, a thrust specific fuel consumption. So when we are considering the jet engine, we consider the thrust specific fuel consumption, okay, especially when we are considering for the jet engine, we specify that in terms of thrust specific fuel consumption, okay. Another factor is the L by D. L by D, in other words, we can call as a aerodynamic efficiency, and you will have some factor of the some kind of weight which will be the which will tell you the fraction of fuel you need to move from one point to another point. That will be the fraction we'll be having, that is a separate. But the main point over here is how this range is directly connected with a specific fuel consumption and the LD. So what it says, that it expresses that better you will have the L by D ratio, okay, better you will have the L by D, better the range that particular aircraft can cover, the maximum range, okay. Then another way to cover the maximum range, either it should have the low TSFC, okay, it should have the specific fuel consumption should be low, then only that particular engine can has a capability to endure to cover large amount of range, then only that aircraft has a can have the capability to cover the large amount of range, okay. Now if I want to talk about again L by D, okay, L by D again has a direct connection with an engine. How? Thrust to weight ratio, okay, thrust to weight ratio. Now yes, now this is the parameters that it may vary sometimes, okay. So for small aircraft it is slightly ranges within this parameter, that is 0.35 to 0.45. For mid-range aircraft it goes within 0.3 to 0.37, and for long range aircrafts the T by W ratio should be 0.2 to 0.33, okay. Now how to find the lift from that, how to find the lift using that values? So again we're considering that at a steady level condition, you will see it in the flight mechanics that T by W equals to 1 by L by D max, okay. This is a formula, okay. How it came? So thrust equals to drag and weight equals to lift. So both, what we are doing here is dividing that, we are getting T by W equals to D by L, T by W equals to 1 by L by D, okay. So we say that at when we have the thrust requirement, will give that W by L by D max, okay. So when you're designing, even when you're designing any aircraft or selecting the suitable engines for your aircraft, again you need to figure out how much lift to drag are going to fix the issue of your propulsive efficiency, and also how whether it is really suitable to cover certain amount of range that your aircraft has already missioned for it. Okay.
Mom,
Yes.
we have to choose this L by D after getting the calculation of L by D max. We have to choose the airfoil, mom. Like, is it like that?
See, here we are talking about aircraft. Okay. Now there are lot many factors. If you want to find the L by D, first when you're finding, you will be finding for to select the best suitable for airfoil. First we find for the aircraft, then we find for the wing, then we find for the airfoil. Step by step is there, right? So when you go for, if I say for the uh, aircraft, the gradually the L by D will increase, because for 2D the L by D will be more as compared with the wing. So as we find out, the gradually my lift coefficient has to come here. So this is the value which we are talking about here is the aircraft. Okay, we cannot find out directly, and this formula what we are expanding, we are talking for an aircraft. Okay, this is an overall aircraft. There is a difference between the this lift to drag ratio for an airfoil, for a wing, and for the entire aircraft. Okay.
Okay, mom.
Yeah.
What do we do after finding this L by D, mom?
I am not getting this point. See, after finding this L by D, we are going to put it over here, right? If L by D value is more, then other terms are constant, right? Then definitely
Yes.
you can provide
Increase
a
the range.
better range, right? So automatically, and how this is connected? This is connected in this method. The thrust produced by in the engine, okay, with the total weight of the aircraft. This is not the weight of the engine. This is the total weight of the aircraft by the lift produced by the aircraft, and so on.
Okay,
Similarly,
okay.
in some problems, they can also ask you like that, how this you might have to use this formula also, like you have done in flight mechanics. Okay, so we will also solve one of the problem something relevant to like flight mechanics, and how they have implemented that concept in the propulsion. Okay, we will look into that also. I think we have covered. Yes, it's very important. This is the same image that we were discussing over there. One more important topic we have is a afterburning. Okay, afterburner. Yes, before going for afterburner, we have to see how this uh, the performance factor varies with the turbofan. Okay, because turbofan, the very important parameter we have is a bypass ratio. Okay, bypass ratio. Now what is bypass ratio? That mass flow rate of the bypass by the mass flow rate of the core. Okay, now can I say the mass flow rate of the total mass flow rate will be mass flow rate of the core plus the mass flow rate of the bypass. Alright, now here it shows that in the graph A, what happens, and certain amount of bypass ratio, they at certain amount, it is fixed, means let's consider it is 2 bypass ratio, right? What happens as we increase the specific thrust, right, at some point it decreases, and then again by further increase in specific thrust it increases the SFC. So initially what happens, as we increase the specific thrust, okay, at a certain amount of bypass ratio, the specific fuel consumption decreases, After it reached to a minimum level of SFC, it again with further increase in specific thrust, the SFC increases. Second important point is, as we increase the bypass ratio, now tell me from this figure what do you understand? Now what do you understand from this figure? This figure B. In figure B, what it says?
When the bypass ratio is increasing, the SFC is also increasing, ma'am.
As increase in bypass ratio,
The SFC is increasing, ma'am, from the graph.
how? See, if I look into the
SFC and thrust both are decreasing.
Yes, it is decreasing. See this point. See the
Okay,
minimum
okay. It's a
point.
reverse arrow mark. Okay, okay,
Yes,
okay.
yes. It is a reverse arrow mark, right? So if I consider
Sure,
this is
sure.
graph A, B and C. So I can say this is a point A, B and C. So what is happening? The SFC decreases, right? So what I suggest is that you just remember the graph, right? Once you remember the graph, it will be very easy for you to analyze the parameter, because if you remember increase decrease here and there, it is confusing, right? So it's better, it's a kind of suggestive thing. You remember the graph or the nature of the graph, so it will be, by seeing the graph you can able to find out or connect between the parameters. Okay, so here in this graph it shows that from A to C it is increase in bypass ratio. So what is happening? The SFC is drastically falling as increase in bypass ratio. Okay, now another one we have, let's see how it forms with an inlet temperature. With an inlet temperature, what it does, inlet temperature. So what you can understand in the inlet temperature here, what is happening? If we are increasing the inlet temperature with increase in fan pressure ratio, sometimes fan pressure ratio, and in ideal case fan pressure ratio is equal to the bypass ratio. Okay, fan pressure ratio is equal to the bypass ratio. Now in case of that, okay, increase in turbine inlet temperature, what is happening with an specific thrust? Fs means specific thrust. What is happening in the specific thrust? It is increasing. The specific thrust is increasing. Now what is happening with the SFC?
SFC is coming down now.
SFC is slightly reducing down. Okay, SFC slightly reducing down. Alright, now another important we have is on thrust augmentation. So here already you know what is meant by thrust augmentation. That means here this is a general turbojet engine, okay, where we have inlet, compressor, high pressure compressor we have, then followed with combustion chamber, then turbine, then nozzle. Now what happens? Why we need thrust augmentation? To improve the thrust. So how we can improve? There are lot many ways. One of the way is to keep another flame holder. You can see another flame holder at the exit of the turbine. So whenever the hot air gas expel out from the combustion chamber, right, again it get combusted and here it get expels out. Now using this method they improvise the thrust. Now if I have to draw in graph, how I can draw? Drastically the thrust was increasing at increase in velocity. At some point the thrust was increasing velocity. Once I ignited or switched on my thrust, it will be at the same velocity, the thrust will be hiking. The same velocity thrust will be hiking. So there will be of, this is still the off one. Once on, it will be hiking upwards. It will be hiking upward. Now here also lot many types are there. Okay, lot many types. That types all theoretical. I'm not going much into the theoretical part. I'm just the notes I'm providing over here, that what are the theoretical part and how they are doing those things working. So apart from that, understanding the working, it is very important how they are interconnected with an performance point of view. Okay, so you can see in this particular image, right? So with respect to time and with respect to altitude, so you can see if the flight has to reach at this altitude, right? So using afterburner and without afterburner concept, so what you can understand, before let me explaining this, what do you understand from this figure with afterburner and without afterburner?
The altitude can be achieved very quickly
The altitude can be achieved very quickly.
with respect to that afterburner, ma'am.
Yes. And what else? The altitude?
The flight time will be definitely reduced, ma'am.
Yes. Second is the flight time will be reduced, and the rate of climb will be high, right? And the position or the target of point of reaching will be much faster as compared with the without afterburner, right? Okay. Now what are the factors? Are some important factors that you have to remember. Okay, so increase of turbine inlet, increase of turbine, so increase in turbine inlet temperature, that is T03, if increases, it will also lead to an increase in specific thrust. So if they increase the specific thrust requirement is getting more, then on the same note we have to remember the thrust for a given engine size has to be more or less. Okay, has to be more or less. If the temperature is getting high, right, exit temperature is high, similarly the specific thrust will also be high. Okay, so what will happen? What will happen with the thrust? What will happen with the thrust? Engine size. Here they have given at the engine size, okay, at the constant engine size. If the turbine pressure, turbine inlet temperature increases, specific thrust increases. But if we increase the engine size, what will happen? What will happen if I increasing the size of the engine? In other words, if I am increasing the size of the engine, suppose, what is meant by size of the engine if I am increasing?
Ma'am, the amount of thrust that is produced can be increased, ma'am, by using the bypass.
Alright.
The engine size is going to be increased, the bypass can be increased, ma'am.
So now if I say like I want to increase my size, I will increase the power for sure, but how will you, again you have to keep that in mind, that how will you overcome the weight? How will you overcome the weight of the engine, right? Again you have to keep that in mind. So if you have to overcome the weight, again That means if the engine is overweighted, again your turbine inlet pressure will be going high. If the turbine, in that case, if the turbine inlet pressure goes high, that means fuel consumption or the requirement will be more. Your specific thrust will go down. On that case, your specific thrust will go down. You got the connectivity? Could you able to get the connectivity? If your engine size goes high, right, it will create more amount of weight. The weight will increase, right? If the weight increase, you need more power. Power requirement is more to propel and move forward, right? When we need power, that means you need more amount of fuel. That is, your SFC is high. If the SFC is high, means you have the low specific thrust. Can I say that? Can I say that?
Yes, ma'am.
Alright. So it is very much important to understand the connectivity. Okay. So
Ma'am, then why it is written it will increase the specific thrust when we increase
no,
the
no,
inlet
no.
temperature?
At a given size, size is fixed. Size is fixed.
Oh,
Now this is thing you have to remember. Sometimes they might give you some small kind of problem, right? So they might give afterburner and non-afterburner velocity. So they might find out what will be the ratios or either vice versa. Okay. So with and without. So near about the ratio depends on approximately 1.5 times. Okay, 1.5 times. Okay. Now another one we have is that how this afterburner temperature ratio, okay, varies with the pressure loss. Okay, varies with the pressure loss. Now, so it is again very simple to understand, right? With a different kind of pressure ratio varying from 1 to 2, okay, 1 point to 2 point. Okay, it is varying. So with increase in afterburner temperature ratio, so gradually if the temperature ratio keep on increasing, the pressure losses, the chances of pressure losses are quite higher. Okay, and these are the different kind of inlet Mach numbers. So as the inlet Mach number increases, okay, with an increase in afterburner temperature ratio, the pressure losses are quite higher. Okay, are quite higher. Okay, this is another question might come about the pressure loss within the afterburner. Is that clear over here? It's clear. Now shall we move to the problematic part? Yes,
Can
yes.
you please repeat this again, ma'am? Momentum pressure loss.
Okay. Now you can see, let me, this is the direction. We have the afterburner temperature ratio. Here we have the pressure loss. Okay, pressure loss. Now we can simply say in one statement that as we increase the afterburner temperature ratio, there will be increase in pressure loss. The pressure loss is going to increase gradually, right? It is increasing. It is in positive curve. So increase in T06 by T04, which will leads to increase in pressure loss, which will also leads to an increase in pressure loss, right? Now how it happens with an variation with an inlet Mach number, with an inlet Mach number. So if the inlet Mach number, right, if as we increase the inlet Mach number with an variation of temperature ratio, variation of temperature ratio, what we can see, if I want to increase my Mach number, it is increasing likewise. So in this point I can say that comparing this point and this point, so I can say that gradually as I'm increasing my Mach number, inlet Mach number, with increase in afterburner temperature, which also will leads to an increase in pressure loss. Okay. Also it will leads to an increase in pressure loss. Clear?
Yes, ma'am.
Okay. Now we will move to the numerical part. Okay, numerical part. So, okay, we'll start with a very basic thing. Okay, so let me read the question. A turbojet power aircraft is flying at Mach number 0.8 at an altitude of 10 km. The inlet and the exit areas of the engine are 0.7 meter square and 0.4 meter square respectively. The exhaust gas have velocity of 500 meter per second and temperature of 60 kilopascal. The free stream pressure, density and speed of sound are given respectively. Okay. The thrust of the engine in terms of kilonewton. Okay, thrust has been given and you have to find in terms of kilonewton. Alright. So what you have to find is, here is thrust. Mach number is given, that is flying Mach number, that is V we can obtain, that is I can write MA. Okay, I can write MA at an altitude this. That means A inlet is given and this one exit is given, VE is given, PE is given, right? Free stream velocity has been given, P infinity, rho infinity, infinity has been given. How will you find this? So first, thrust they have given. What is the formula? ME VE minus M dot A VA, right? So here they have not used anything about the fuel, so I have neglected that, plus AE PE minus PA. This is a general formula, right? Since again ME and MA will be again not, the fuel is not given, so I can take M dot VE minus VA plus AE PE minus PA. Okay. So how I can find VA? VA I can use this MA value, VA by A. Now they have given free stream velocity, so I can use that. So VA equals to M is 0.8 into 299.5. You will get in terms of meter per second. So this is given, this is found out. AE is given, PE is also given, P they have given free stream, so this is also given. Now from here, how to find M dot? How to find M dot? Can I use
ma'am.
yes, yes.
239.6.
Answer?
No, I'm telling that that's volume VA.
Okay, VA is
239.6.
okay. So M can I use based on the continuity equation, like rho AV? Can I use that concept, rho AV, because rho value is also given. Let's consider for the inlet one. Okay, A is just now we found out. Okay, free stream. So 0.413 into 0.7 into 239.6. Then substitute over here, substitute the value over here, and you will get the T value. Just let me know the answer.
69 point. Just a minute. 69.29 ma'am. 27.
Which one? 69? Mass flow rate.
0.27. Yes ma'am. Yes ma'am. It's mass flow rate.
Okay, 69.27
27 kg per second.
Alright. Now substitute the value over here and we will get the thrust value.
Um, 180.33. 18033 kilonewton.
8033.
180. 180.
See, you have forgotten this part, I think. We have the AE P minus P infinity we have.
It's kilonewton.
See, are you getting the same value?
I'm getting it as 31.438
Yes,
kilonewton.
31.43.
38
Yes, it is in terms of Newton, right?
kilonewton. I'm telling ma'am. 31.438 kilonewton.
Are you sure? I am getting
Yes, ma'am, it's
31.4 kilonewton. This is the
That
answer.
is almost.
See, it is the here they have given in kilopascal. Have you converted that in terms of Pascal?
Yes ma'am.
Ma'am, 31.419 kilonewton.
Ha, this is the right answer. Please check your answer, because here we have the kilopascal. Here also we will have kilopascal. Where is it? Yeah. Okay. So when you will get something value like 31438 Newton. Okay. So in terms of kilopascal, you will get 31.4, and in the answer ranges between, they have given is 29 to 32 kilonewton. They have given this answer. Okay. All right. I think we have done this problem. I think morning we have done this problem. Okay. So yes, this is a different kind of problem. The diameter of propeller of an aircraft is 2.5 meter. It flies at a speed of 500 km per hour at an altitude of 8,000 meter. For a flight to the jet speed ratio of 0.75, determine the flow rate of air through the propeller. Okay. Second, you have to find is thrust produced, specific thrust, specific impulse, and thrust power. Now how do you find? Diameter of the propeller has been given, and flies at a speed VA is given, altitude is given. Alright, so here I need to give you some parameters. Since the altitude is given, yes, the density of the altitude has been given at 8,000 meter. Density is 0.525 kg per meter cube. Okay, then they have given the flight to jet, that is speed ratio has been given, and you have to find the flow rate of the air through the propeller. Okay, flow rate means what? The mass flow rate. That means you have to find the mass flow rate at the propeller. Okay, thrust specific impulsion. How do you find? What is mass flow rate of the propeller? Rho a v. Now which velocity will you take? Will you take inlet velocity or will you take the jet velocity?
The inlet.
At the blade side, ma'am. Where the blade means from the blade side, ma'am. Entering.
We have already said in the morning, if they have given some kind of propeller and they have given the upstream and downstream, let's consider the flight and the jet, they have given the upstream and downstream. That means upstream, okay, that is VA is given 5000 kilometer per hour, that is the upstream one, and downstream you can find VA by VE has been
V1
given
plus
as
V2 by 2.
exactly. So you can find out. So V means VA plus VE by 2. That value you have to take. Okay, that will be the value you have to consider. Density is known to you. Okay, A you can find because diameter is given. To find out the area, how will you use? Pi by 4 into d square. You will find the area. Velocity you will find using this formula. Okay. So do not forget to convert the kilometer per hour into meter per second. Okay, meter per second. So how do you convert? 500 into 5 by 18. Okay. Similarly, to find VE, you just need 500 into 5 by 18 by 0.75. We will get the VE value.
I'm 161.
Which one is 161?
V, ma'am, V. V.
160?
1.4.
Okay. Okay. So you can find out the mass flow rate here then. What is rho? Rho is
417.3.
I'm getting it's 162, mum. Is that point variation considered?
that is not an issue.
Okay.
So 417.3 is an airport answer. Alright, so first one you have found out, then next one, this is done. Next one we have the thrust produced. Now how to find thrust produced? T equals to m dot VE minus VA. Now mass flow rate is found out. VE also you know, VA is also known to you. Just substitute.
It's 19.362 kilonewton.
Yes. Okay. Now this is also done. Thrust produced is done. Specific thrust. Mass flow rate.
46.38 more.
46.38
46.38.
Newton per kg per second. Okay. How you find specific input? You can divide the
The specific thrust by gravity.
Gravity. You can find. Okay.
4.727 seconds.
4.727 seconds. Okay. Next we have thrust power. Thrust power means thrust into velocity, that is VA, right?
It's 2.687 megawatt.
Megawatt
2.687.
2.687 megawatt. Okay. All right. Okay, this is done. Now it is a similar kind. We will come to this problem later on if we have. Let's move to another different kind of problem. Okay, let's solve this problem. Okay, a turbojet engine operating with an exhaust nozzle nozzle unchoked propels an aircraft at a uniform speed of 900 km per hour. It develops a thrust of 14 kN when the jet speed is 1500 km per hour. Calculate the enthalpy change in the exhaust nozzle if the nozzle efficiency is 0.95 and also find the specific thrust of the engine. Okay. So here what are the things I have given? Operates VA is given, thrust is given, jet VE is given, enthalpy change in the nozzle, and here they have given the nozzle efficiency. Also find the specific thrust of the engine. Okay. Two things they have to find. So first of all, you change this kilometer per hour to meter per second. V is given, then P is given 14 kilonewton, theta n is given 0.95. Now efficiency is given, right? So let's see what is nozzle efficiency. Actual change in enthalpy by ideal change in enthalpy, remember? So if I want to draw the diagram, something like this is a point where we have 3, this was a 0.4 and this was a 0.5. Nozzle we are considering from 4 to 5, right? So this was the actual means T naught 4 minus T naught 5, T naught 4 minus T naught 5 prime. Okay, so if I can write in also this way, del H by del H hash. Can I write in this way? Now one more thing, we have said in the graphical representation that difference of this T naught 4 minus T naught 5 is equals to VE square by 2 CP. Can I say like that? T naught 4 minus T naught 5 equals to VE square by 2 CP. Can I say this?
Yes, ma'am.
Yes, ma'am.
Now, can I say this is equals to del H? Can I say this is equal to del H? Can I say that? So
Yes,
T
ma'am.
naught
Yes, ma'am.
4 minus T naught 5 equals to twice of del H so let me write over here. So VE square by 2 CP by T naught 4 minus T naught 5. So keeping this VE square by 2 CP into T naught 4 minus T naught 5 prime. So this is also become del T, which is what? Cp into del T becomes also del H. Okay, del H. So what I can write here, eta nozzle equals to VE square by 2 by del H S. So this is what we need to find. So del H S equals to VE square by 2 by eta n. Substitute the value of this VE. What is VE? It is around 15 into 5 by 18 whole square by 2 into 0.95. So you will get enthalpy change in the exhaust nozzle. Yes, yes.
How do we know that if they are asking about actual enthalpy change or ideal enthalpy change?
Well, these are the things you have to, when you practice, you have to, you know, get used to with that question, that how to find out this thing. Okay, once you practice, you will know that that in this question what they are trying, enthalpy, because that's a good question. Here in this question they have not said whether it's ideal or it's an actual one, because here what we are finding is an ideal one, right? So by based on the practice you have to understand. Yes.
Is it 91,374?
Just let me look into the answer. 9
91374.
Yes. Yes. Del H equals to 91374.995. 27, I think 27
Yes, ma'am.
joule per kg. Now this part is done, right? Enthalpy change is done. Now next what we have to find is specific thrust. Okay, so how do you find specific thrust? What is the formula
F by
for
m
this?
dot a.
What is specific thrust formula? Is m
F.
dot,
F by m dot m.
yeah, F by m dot a. Now what is F? M dot a by VE minus V.
Can also use a velocity difference in inlet and
Yes, yes,
exit,
yes.
ma'am.
Yes, yes, both are same. That only I am showing. See, both are same. It will get cancelled off. So we will get VE minus VA. Okay, the difference in velocity. So velocity is given, difference. So you can find out.
One 66.67.
Okay, that's excellent. 166.67. Sorry, there were some internet issues from my end. So the answer was 166 point. Okay, sorry, there is some internet issue from my end. Okay. So answer was 166.67. Unit should be Newton per kg per second. Alright. So yes, this is another different kind of problem. So what this question says that a turbojet engine propels an aircraft at a speed of 900 km per hour. When it develops a thrust of 14 kN, the air intake to the engine is 50 kg per second and air fuel ratio is 85. The calorific value of the fuel supplied to the engine is 44,000 kilojoule per kg. The isentropic enthalpy change in the nozzle is 1150 kilojoule per kg. Find the thrust, thrust power, propulsive power, then propulsive efficiency, thermal efficiency and overall engine efficiency. Okay. So again you need to figure out what are the given values, given data. Okay, this is the thrust, then this is the mass flow rate of the air intake, this is the fuel, this is the air fuel ratio. Okay, so air fuel ratio, calorific value is CV, isentropic change in nozzle they have given, Now find the thrust. Now first we have given thrust. So what is thrust? M E V E minus M dot A V A, because here they have given a term in terms of air fuel ratio, so I have to use that this formula right now. Other times that the pressure thrust I will be ignoring because that values has been not been given,
Mom,
so I will ignore that. Yes, please.
they've already given the developed thrust is 14 kilonewton, no?
Huh?
They have also asked us to find the thrust too.
Okay. Right. All right. So you can ignore that, right? So you can ignore that. That's a good point.
Okay, ma'am.
So okay, let's find the thrust power. This one into VA. Okay, this one into VA will give the thrust power, right? So how to find M dot E is a mass flow rate of air plus mass flow rate of fuel. Okay. Now here they have given mass flow rate of air by mass flow rate of fuel has been given as 85. So if I take mass flow rate of the fuel common outside, M dot of A by M dot of F plus 1, so I will get M dot of F. I can take in a reverse way because M dot A is given, so I can take in this way common 1 plus M dot of F by M dot of A. So mass flow rate of fuel has been given is 50, then 1 plus 1 by 85. So when you solve, you get M dot E then okay, how to find this VE? VE is given.
The thrust is already given. So using the thrust, we can find the V.
Exactly. So using the thrust, you can find M dot E VE minus M dot A VA. Okay, 14 into 10 power 3 equals to whatever the value. Now what is VE?
Ma'am, can't we directly use that thrust value for calculating power thrust?
But power thrust you need to calculate, right? That is not given, power thrust.
Ma'am, but
See, power
thrust is given na 14 kilonewton.
Yeah, right, very good. Yes, thrust is given into VA is there, right? So 14 into
VA 900 kilometers per hour.
It's actually 523.8.
how much you're getting?
I was telling the VE value on the exit velocity.
3.5 megawatt.
VE is
523.84 meters per second.
okay. 5
23.84.
okay, meter per second. Okay. So you can use that. And what is
3.5
PT value?
megawatt.
It's 3.5
3.5
megawatts.
megawatt.
5 megawatt. Okay. So what is propulsive efficiency?
Propulsion.
Okay. Power. This propulsive power. Before that you have propulsive power. P dot P, right? What was the propulsive power formula? P E. Just tell me the formula. Something we had half. Just let me know the propulsive power formula.
It's actually the thrust power plus the absolute kinetic energy.
Hmm.
From half m dot a bracket में v square minus va square.
M dot A है.
Yes ma'am. M dot a upon 2 in bracket में
Okay,
v square minus v square.
Okay, that means this will be the formula. So that is for when the fuel fraction is taken as 0. Okay. Then this is the formula. Since here fuel fraction is considered, so we have to use 1 plus of F. Okay. Just like thrust. This is the formula, 1 plus of F. What is the value you are getting?
Then is it 5.37 megawatt?
Yes, near about 6 it is.
37
5.37
megawatt.
Alright. Next we have propulsive power. So propulsive power, you know, it is by PT by PP. Okay, PT is a thrust power and by the propulsive power. So both the value you have found out, 3.5 divided by 5.37. Now in this thing we can also state one more factor.
Propulsive efficiency, right, ma'am? We have to find right now.
Propulsive, yes, propulsive efficiency.
So we can
Is
use
between the
2 alpha by 1 plus alpha also we can use.
you can use either of that, anything, because alpha value is see here
Not
again
given.
you have to find out the alpha and you have to utilize that, but here you have found out both the thrust power and the propulsive power. Anything you can choose, right? But one more thing you can conclude from this particular expression, we can say that to have the highest or we can to obtain the 100% propulsive efficiency, that means we have to make the thrust power has to be equal to the propulsive power, right? That also we can state likewise. So what is the value you are getting? Propulsive efficiency
0.65.
0.65, right? That means 65%. Then thermal efficiency. From here you can find thermal efficiency. Thermal efficiency is propulsive power by the heat added, that is m dot of F into CV.
Twenty 20.75%, ma'am.
How much? 20?
20.75%.
Next we have overall efficiency is a product of propulsive efficiency into thermal efficiency.
It's 13, ma'am. Approximately 13.
Yes, it is showing 14 in my answer. Okay, you can give 13%. So mine it is showing 14.7.
Okay.
Alright, so now we will have okay, this is another very typical kind of problem, okay, which I was telling, which is somewhat relevant to flight mechanics. Now see this question. An airplane propelled by a turbojet engine has a flight speed of 800 km per hour at an altitude of 10,000 meter. The drag coefficient for the plane is 0.016 and has a wing area of 20 meters square. The effective jet velocity is 460 meter per second. Determine specific thrust, air consumption of engine, density at they have given that 10,000 altitude is given. Okay. Now see what are the parameters has been given. Flight speed has been given, CD has been given, S has been given, span, wing span denoted by capital S, VE has been given, jet velocity has been given, okay, density at that particular altitude has been given. Now what we need to find is specific thrust. Now what is specific thrust? Is the thrust by mass flow rate of air, right? Now they are given the density, that the drag coefficient and other parameters they are given. Now what we can use that formula, and how to find out the parameters. How to find out?
To proceed
Now what is,
we have the.
there is another formula.
Okay, ma'am.
This is the thing. Another formula is there. Can we proceed with that?
Simply speaking, yes, ma'am. Both the M dot A's will be
Yeah.
cancelled.
M dot will be cancelled. We can substitute that. So let me know. This is in kilometer per hour. So
237.78.
237.78. 278 meter per second. So you have here 460 minus 237.
Ma'am, final answer is 237.8.
No, mom. That was 222.22, mom. Sorry, I told the final answer.
Okay, 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 okay. All right. So okay. So answer was 220.
222.2.
Okay. Okay. So you get us something
237.77.
Okay. So this is the for the specific thrust. All right. Now, sorry, the unit is Newton second per kg. Okay. Now, how to find air consumed of the engine? That means we need to find out the mass flow rate. Now, how to find the mass flow rate? How to find out the mass flow rate? Huh? Sorry. Mass flow rate. What are the formulas you know? Rho. Huh. Huh. So how can you find A? What is the A?
Given ma'am already.
This is the wing area. Do you think what is area? That means cross sectional area. So if that means air is flowing, entering into somewhere, right, and leaving out somewhere. That is a surface area we can say, right? Can we use that? Any other?
No.
Any other scope?
No.
No, I don't.
Okay, why we have given the drag?
That's
We have given CD value.
Thrust
Drag
required
polar
equals to
equation.
drag, ma'am.
See,
Required
CD
equals to
drag
drag.
polar equation. Okay, that's good.
CD not plus KC.
See, we are not talking about this here. Okay, this is a drag polar equation, but they have given. Can we say the drag equals to thrust equals to half rho v square s CD? Can I use this formula?
Ma'am,
Rho
but
is
this is
given.
at the steady level condition, ma'am.
Yes.
And it is not given
Yeah.
that flow is steady.
Steady level is not given, but we can use this formula. Can we? This is thrust requirement.
Yes,
Thrust
ma'am.
requirement equals to drag. Okay. See, even in nowhere it will be written that lift is equals to weight, but we do consider in stalling conditions and other conditions. Okay. So, using that, half rho is given, v is given, right? S is given, CD is given. Now, whatever, again recalling, Fs equals to T by m dot A. Now, T you got, okay, thrust, you got the value, okay. Fs you know the value. Now, from there, can you find out this m dot? Thrust you will get from here, right? Thrust value you will get it from here. So from this you will get what is the m dot. So sometimes, see why we are solving some kind of very different kind of problem, because we will get an idea that these what are the possible ways that they ask the question. So some conditions you have to assume something and you have to solve the problem. Okay. Now one more benefit you have in this MCQ pattern, you have the options. So once you see that if this way you can find the answer, that means you are going in the right track. Okay. So what is the thrust value you are getting?
Density, ma'am.
Density is given here. 0.41356.
3,567.5.
3000. Okay, 3005.
3,567.5.
Okay, I am getting around
Ma'am,
4135.
ma'am,
I don't know, just ensure that my calculation shows that I'm getting 4135 Newton.
Ma'am, mass flow rate is 0.071.
Mass flow rate just point 0.
Mm,
No, I'm getting 17.4 kg per second. Just ensure that whether my these values are right or wrong. I'm getting these other values.
yes, ma'am. 0.072 mass flow rate.
Point zero
72.
072.
yes, ma'am,
Yes, ma'am.
yes, ma'am,
But I'm not getting. See how you're getting that. See, thrust you're getting around 4135, right? Divided
Ma'am,
by this value. It has to get something divided by
I'm getting
2375.
15, ma'am. 15 kg per second.
Okay.
So what's the actual answer, ma'am?
It is ranging from 15 to 18.
Okay. I'm exactly getting 15.
It is ranging within that. Because I solve it is I'm getting 17.4.
I'm 13.7, ma'am.
30.
13, 1, 1, 3, ma'am.
13 point.
7.
Uh-huh. So, alright, it is somewhat nearby um, this range, but they have given 15 to 18. So, no problem.
ma'am.
The
Already I'm getting
yes,
13.74, ma'am.
13.
13.7.
Okay. No issue. That may be some error in that parameters here in the density, right? So some may have taken two decimal places. That's why that error is coming. Okay, that's not a big deal, right? So you can expect such kind of questions. Okay. Yes. Now let's solve for the first question. Which one of the following engines should be used by a supersonic passenger transport airplane for a minimum specific fuel consumption? Okay. So do not unmute yourself. I am launching a poll. Okay. I'll be launching a poll. So please respond from the poll. For the first one, which one of the following engines should be used by a supersonic passenger transport aircraft for a minimum specific fuel consumption? Okay, you can answer through the poll. Alright, so okay, almost all are getting the right answer. So you remember what I said, like we had some kind of specific impulse with increase in Mach number, right? So in that graph it was clearly stated on all the parameters. The biggest one we had was a turbojet. Then we have the turbojet engine with afterburner, right? So this is the right answer. Okay, and that's great, the majority have given the right answer. Moving to the next one, we have is the next question. Okay, we have the rocket question. No, we will do this question later on because we have not done the rocket yet now. Okay, next question we have. A turbofan engine has a bypass ratio of 5 and total mass flow rate of 120 kg per second. Then what will be the mass flow rate through the bypass duct? Okay, find out, and let me again launch a poll. Solve carefully. Solve it carefully. Solve it carefully. Abhijit and Samarth, solve it carefully. Mohan Kumar, solve it carefully. See what they have asked in the question. They have given bypass ratio. Okay, bypass ratio. Okay, what is bypass ratio? It is a ratio between the mass flow rate of a bypass by the mass flow rate of the main core, right? Main core. Then here what they have given, the total mass flow rate has been given. Read the question carefully, do not hurry. Mass flow rate of the total means what? The mass flow rate of the bypass by the mass flow rate of the core. Did you get it? Mass flow rate of the bypass plus the mass flow rate of the core will give the total mass flow rate, that is equals to 120 kg per second. Right? Did you get it? Now tell me how to solve. So I can write likewise 5 equals to mass flow rate of the bypass, mass flow rate of the core. Now mass flow rate equals to, that is 120 equals to mass flow rate of the bypass plus mass flow rate of the core. Now we need to find what is the mass flow rate in the bypass in terms of B. So I can take B.
It's 100, ma'am. It's 100, ma'am.
It's 100. Yes. Option B. Okay. So I can get something equation like this. Then B we need to find. We know m dot C by m dot B equals to 1 by 5. So we can substitute that 1 by B equals to 1 plus 1 by 5. When you resolve that equation, you get m dot B equals to 100 kg per second. Did you understood that? Did you understood your mistake?
Yes, ma'am. Yes, ma'am.
All right. Okay. Another different kind of question. This is the question from the ramjet. Okay. An ideal ramjet engine is flying at a Mach number m. Okay. The exhaust gas static temperature at an outlet of the nozzle is TE. The ambient static temperature is TA. The gas constant R and the specific heat ratio gamma do not vary throughout the ramjet. Assuming the nozzle exhaust static pressure is equal to the ambient pressure and the fuel air ratio, that is F, is very less than 1, then what will be the thrust per unit mass flow rate? Okay. T by mass flow rate. And what is the given? PA is equals to PE. Which among this answer is correct? Again, let me launch the poll. Okay, again I have launched the poll. Anybody have completed? Please do recheck it once again. You want me to solve this one?
No, ma'am. No, ma'am.
Okay.
Mom, we are trying. Mom, we are trying.
Okay. First, I'm giving the hint. Okay. What they are asking? Thrust per mass flow rate. Right? Now, what is thrust per mass flow rate? Here the fuel is 0. Ignore it. Okay. So, we can write VE minus VA. Okay. This is a ramjet. What they are telling, T at the ambient is equals to the exhaust. So in the ramjet, what is the main assumptions over here? Mi equals to Me. Now this is a clue, and from here you find out the answer.
Ma'am, I type on the wrong option. By mistake.
Okay. So Mi equals to Me equals to M. Okay, if I take, let me take common M. Common is R, gamma R root over, we'll take it common, root over Te minus root over Ta. Okay. Now we have something divided by divided of something. Now we have Te divided by Ta in this options. So what I'm going to do is M gamma R, I will take root over Ta common. So what I will get, Te by Ta minus 1, and which is shows the right option is option C. Okay, all right, it's clear to all of you how I have
Yes,
done.
ma'am. Yes, ma'am.
See the gate, the simple thing, you know the concept, you know the formula. You can see in this question that how twisted way they will ask you. This is what the gate, the simple question they will ask in a twisted form. Okay, next we have this is a very simple question. Let me launch the poll. Let me launch the poll again. It's a propulsive efficiency of the turbojet engine moving at a velocity and having the exhaust velocity with respect to the engine will be given by. That means instead of having VA we have V infinity, okay, U infinity, and instead of VE we have the U infinity, sorry, UE. So what was the formula? Propulsive efficiency of the turbojet is 2 sigma by sigma plus 1. What is sigma? VA by VE. That, so you need to remember the formula, or I can say twice of VA equals to VE plus VA. So the right option is option D. Okay. Now this is another important question from ramjet. Okay. An ideal ramjet is flying at an altitude of 10 km with a velocity of 1 km per second. The ambient pressure is 0.25 bar and temperature is 225 Kelvin. The exhaust gas from the engine are optimally expanded and leave the nozzle at 900 Kelvin if the specific heat ratio remains constant. The specific thrust developed by the engine is approximately. So here also I am launching the poll.
Excuse me, ma'am.
Alright.
I'm not
So
get.
I
I'm
got
excuse me, ma'am.
disconnected. Yeah, I
I'm
got
not get.
disconnected. Sorry.
But I
Okay.
didn't get
Yeah,
the
tell
poll,
me.
ma'am. But I didn't get the poll, ma'am.
Okay, because I
Okay,
got
okay, okay,
disconnected
sure.
now, so I couldn't launch
Okay,
the
okay,
poll.
okay, sure.
All right. All right.
Excuse me, ma'am. May I tell a small
Yes,
suggestion?
please.
May I tell a small suggestion? Actually, at
Yeah,
5
yeah,
o'clock we are having
sure.
our internship session,
Actually,
ma'am. 5 o'clock we are having our internship session, ma'am. So,
Okay.
yes, ma'am. Today only, ma'am.
Today?
So, can we
Okay,
please
okay, okay.
find it?
So actually internship na
Can we
fully
please
kitchen sir
find
is
it?
looking. Yeah, sure. Actually, definitely. Definitely.
I didn't even have
Yes,
my
because
lunch,
internship
ma'am.
when the
I
classes.
didn't even have my lunch, ma'am.
Oh, please, then you may proceed. This is the last
Okay,
question
okay.
we had. Okay? You have
Okay,
answered
okay.
already, and
Okay,
the
thank
answer
you,
is
ma'am. Thank you very
correct.
much.
Okay, if you have not
Okay, thank
proceeded.
you, ma'am. Thank you
Yeah,
very much.
yeah, please.